Hey calculus. So what we've been doing is we've been leveling up from algebra into the world of calculus. So again, if you don't want to take notes on this part, feel free just watch and observe, and I'll tell you what problems to take notes on. So if we go back to algebra, let me get my pen really quick. So if we go back to algebra and we have a straight line, our goal was to figure out, well, what is the rate of change? In other words, we call this the slope of the line. So what we do is we notice that in a line, the slope is constant. In other words, I can pick 2 points on a unique line and figure out the rate of change. I can go up and right or down and left in this case, or if this was a negative slope, I can go down and right or up and left. But the point of the matter is that there's a pattern with a line, and we like linear equations. So for the sake of argument, let's just say I call the first point x1, y1, and I call the second point x2, y2. So if we have x1, y1, and x2, y2, we can calculate the slope by taking the vertical change over the horizontal change. Whoops, sorry about that. So we can find the vertical change over the horizontal change by this formula. We take the y2 minus y1 over x2 minus x1. So that is how we create the formula to figure out the slope. Okay, so the lighting is a little bit dim, so I'm just going to rotate a little bit. Okay, so now that we know that our goal is to figure out the average rate of change, okay, we like linear equations. They're very simple to figure out because of the fact that they grow or decay at a constant rate. And again, I'm just going to put into a context of why we like them. Let's say I purchase an $800 phone and I spend $40 per month on data and texting. So if I create this linear equation, I establish a relationship between the total amount of money I spent on the phone and the number of months since the purchase of the phone. So if it's an $800 phone and I spend $40 per month, I can calculate the total amount by saying I spend $800 on the phone itself plus $40 per month, X. How much money have I spent after 12 months? Well, it's easy to figure out. It's easy to predict the future. $800 just one time, and then $40 for 12 months. So 800 plus 480 is 1,280. So basically, over the course of 1 year of owning the phone, you actually spend $1,280. Okay? It's very, very easy to predict the future when the growth is linear. Okay, well, let's go with one with decay. So let's say I pick $50. If I put $50 on a Clipper card, in other words, a gift card for the bus in San Francisco, or it could be used for BART and Caltrain. But let's say I'm in San Francisco and I use this to ride the bus. So if I have $50 on a card, I think I actually have a Clipper card right here. I'm sure all of you guys know what it looks like, but just to model it, there we go. So if I load $50 on here and if I beep on the bus and it takes away $2.75 every single time I ride the bus, how much money remains after I take 8 bus rides? So if I model the equation, originally I start with a balance of $50, and as I increase the number of X bus trips, I have $50 and I subtract $2.75 per bus trip. And let's just say I use 8 bus trips in a week. So let's say $2.75 times 8, I lose $22 on my gift card. So that means that I would have $28 remaining after 8 bus rides. And the reason I said 8 bus rides because I was thinking about my college life, where I took the bus four times a week, 4 times to college, 4 times back home. I took a day off of college. I think I had a 3-day weekend in my best semester. But anyway, that's just me reminiscing on the past. But anyway, when we have a linear equation in y equals mx plus b, how do you know? Does it have to be y equals mx plus b? No, but it's really, really helpful when it is. But when you have x and y, be to the first power. In other words, no exponent automatically means it's to the first power. Then the slope is constant. In other words, you can make a line if x and y are to the first power. If y is to the first power and x is x squared, that creates a parabola. If y squared and x squared, if they're both second degree, that creates a circle. Fun fact. But anyway, the point is, if x and y are both first degree variables, that means that that's a line and the slope is constant. Okay? We like lines because it's easy to predict the future when the slope is constant. But the main idea of what we're doing in calculus is, okay, well, how do I calculate slope for nonlinear equations? After all, things curve in our everyday life. How do I predict the future when even the slope changes at every point? I mean, if you've ever run the mile in PE class, I mean, I'm not that great of a runner. I huff and puff at certain points when I run. I walk with my hands behind my head, trying to catch my breath. So my speed changes as I run. In fact, I used to be like really, really passionate about algebraic skills, and now, with the shelter in place, and I'm not making this up when I say this, what the infectious disease doctors are paying attention to are exponential growth and the changes on a daily basis. The only thing in constant in life is change, and that's very profound, I know, but you're going to see why pre-calc and calc are super important for the coronavirus. Anyway, that's neither here nor there, but anyway, so let's say I use this graph, and I use this basic graph of y equals x squared, and I just picked these points. -5, 25, -4, 16, -3, 9, so on and so forth. This is the graph y equals x squared. My goal is to figure out a way to calculate change regardless of the position. And let's look at this from the perspective of Isaac Newton. So let's say I want to figure out what the average rate of change is between x equals 1 and x equals 5. So we're looking at x equals 1 and x equals 5. So what I can do, I've got an orange string, because I was trying to highlight it in pencil, and I didn't want to write so dark that it couldn't be erased, and I didn't want to write so light that it couldn't be seen. So if I write this line between x equals 1 and x equals 5, this is what it would look like. I want to figure out what that equation is. So let me put away the orange string. Okay, so let's take a look. Well, first things first, the 2 points for y equals x squared. So the first point is 1, 1, and the second point is 5, 25. So step 1, well, in order to find the average rate of change, let's label this as x1, y1, x2, y2, and calculate the slope. So now that I've labeled my y2 minus y1, that's going to be 25 minus 1 over 5 minus 1. 25 minus 1 is 24. 5 minus 1 is 4. So the slope between x equals 1 and x equals 5 is 6. Okay? Now that I've got the slope, I can figure out the equation, because I've got a slope and I've got 2 points, in fact. So I like 1, 1. So let's say I choose 1, 1. So then I go into point slope form. And I'm going to convert that into slope intercept form. Well, if I choose x1, y1, y1 is 1, the slope is 6, and x1 is 1. So I'm going to look at this. Are there any double negatives? No. So what I can do is just rewrite this as y minus 1 is equal to, distribute the 6 now, 6x minus 6. Okay, and now I'm going to add 1 on both sides. If I add 1 on both sides of the equation, then my average rate of change is 6, but the line that would connect x equals 1 and x equals 5 would be y equals 6x minus 5, which makes sense. Because if I get my orange string, sorry, it's all bent now and I'm holding it one-handed, x equals 1 and x equals 5, it's a pretty steep line, and it would be somewhere down there. Yeah, y equals 6x minus 5. Yeah, sorry about that. Anyway, let's do some more examples. Let's say I want to figure out the average rate of change between x equals -2 and x equals 4. So if I look again at my graph, x equals -2 and x equals 4, I'm going to connect it with a line and predict what the average rate of change is. So x equals -2 and x equals 4 is going to look like this. We're going to figure out what that linear equation is now. So x equals -2. At -2, y is 4. So -2 comma 4 is 1 point. At x equals 4, y equals 16. So 4 comma 16 is the second point. So what I need to do now is label them x1, y1, and x2, y2, and write the slope formula. Now, I plug in the values. Y2 is 16, y1 is 4, x2 is 4, x1 is -2. So 16 minus 4 is 12. 4 minus -2, that's 4 plus 2, which is 6. So 12 over 6 is 2. So the slope is 2. Okay, I have a choice between which 2 points I like, -2 comma 4 or 4 comma 16. I like 4 comma 16 because there's no double negatives I need to worry about. So let's go into point slope form. So because I have a slope and I pick x1 is 4, y1 is 16, so y minus 16 is equal to 2x minus 4. Any double negatives? No, I don't see any double negatives. So that becomes y minus 16 is equal to 2x minus 8. And then if I add 16 on both sides, y is equal to 2x plus 16. And that is the linear equation that calculates the average rate of change between x equals -2 and x equals 4 for the graph y equals x squared. Okay. Let's do 2 more. Okay. Let's calculate the average rate of change between x equals -3 and x equals 2. Well, if we take a look at the graph, x equals -3 goes to y equals 9, and x equals 2 goes to y equals 4. So it's a little bit of flimsy paper. So if I could just use my pen as the average rate of change, that's what the line is going to look like. We're going to calculate it. I know it's a little bit thicker than the string that I was going to use, but I can't do that one-handed and have it all wave all over the place. So x equals -3. That means that my point is -3 comma 9. And x equals 2. That means x equals 2, y equals 4. I've got my 2 points. Let's calculate the average rate of change. x1, y1, x2, y2. So that means that our slope formula is y2 minus y1 over x2 minus x1. Now let's plug in the pieces. y2 minus y1 over x2 minus x1. y2 is going to be 4. y1 is going to be 9. x2 is going to be 2. x1 is going to be negative 3. So let's see what happens. 4 minus 9 is negative 5. 2 minus negative 3, that's 2 plus 3, which is positive 5. Okay, so the slope, negative 5 divided by 5, that's going to be a slope of negative 1. So if the slope is negative 1 and I've got 2 points to play with, well, I could just choose one of the points and convert that into point-slope form and thus try to convert it into slope-intercept form. So I know I said I didn't like double negatives. I just want to make sure that you guys are comfortable with it. So for the sake of argument, I'm going to pick x equals negative 3, y equals 9. So y minus y1 is equal to mx minus x1. But let's say I pick negative 3 comma 9 this time. Well, if y1 is 9, that'd be y minus 9. So far, so good. And m is negative 1. Okay, not too bad. And x1 is negative 3. So y minus 9, no double negative there. Negative 1, okay, you're fine. But x minus negative 3, that's x plus 3. So now we've converted it successfully into point-slope form. Now I'm going to distribute the slope at m equals negative 1. So then I get y minus 9 is equal to negative 1x. Negative 1 times positive 3 is negative 3. And now I'm gonna try to get y isolated by adding 9 on both sides. So the linear equation that calculates the average rate of change between x equals negative 3 and x equals 2 can be calculated by going down 1, right 1, and crossing the y-intercept 0, 6. Okay, let's do one more, and then I'll show you, well, why am I reviewing this algebra nonsense? Well, it's not nonsense, but I know you guys care about the calculus stuff. Truth be told, this is exactly what we're doing in calculus. We're doing point slope into slope int, but with derivatives. Okay, now I just want to show you this fun one really quick. Well, x equals negative 5 and x equals 5. Just to give you a spoiler as to what the graph looks like. Let's say I connect it. I want to calculate the average rate of change. It's going to be, come on, stay still. It's going to be a horizontal line. Come on, cooperate you. It's going to be a horizontal line. And let's prove it. X equals negative 5 matches up with negative 5 comma 25. X equals 5 matches up with 5 comma 25. X1, Y1, X2, Y2. We've got the slope formula. And let's plug them in. 25 minus 25, and then 5 minus negative 5. Well, 25 minus 25, that is 0. 5 minus negative 5, that is 10. Well, m equals 0 over 10. Well, 0 on top is okay, because 10 times 0 is 0, so that slope is 0, which tells me it's a horizontal line. So now I've got y equals 0x plus 25, because they both share that y value, therefore the y-intercept is 0, 25. You can do point slope into slope int, but I just want to show you That's 0x plus 25, or y equals 25, which creates a horizontal line. Okay? So, without further adu, here's the main idea of what we've been doing. So suppose you have a curve, and you only care about the rate of change between x equals a and x equals b. So you calculate the endpoint over here. Let me get the blue. So if I bound the curve at a comma f of a and b comma f of b, right? And I mean these like endpoints on a curve. And I want to calculate the average rate of change. Here we go. We define this as the secant line between x equals a and x equals b. It's not cooperating. I got to do it the old-fashioned way. So we call the connection between x equals a and x equals b a secant line. There we go. So the unique line that calculates the average rate of change is called the secant line. And that's what we've been doing today. But, spoiler alert, that's not calculus. Well, I mean, it is part of the calculus curriculum to find the secant line between x equals a and x equals b. But, spoiler alert, Isaac Newton says not good enough. What happens? I want to find instantaneous slope. In other words, he understands that this is a weird-looking curve, and there's a slope that's completely different throughout the whole course of the curve. In other words, if I were to calculate the slope at various points on the curve, I can't really do that because it's not linear. But Isaac Newton exploited a loophole. He said, okay, well, what if I zoom in closer and closer and closer? So let's just say I want to calculate the velocity at x equals a. Well, who's to say that I can't do the slope between x equals a and a plus 1? Or you know what? Let's make the gap even smaller and smaller. So what you're doing is you're calculating a secant line at smaller and smaller intervals. And in the next unit, we're going to be talking about, well, what's that called? Well, it's called a tangent line. And I'm excited to show that to you tomorrow.